All right, so here is our last short for our second one, and it's just a breakdown of rational exponents. So exponents that are exponents that are fractions, and positive and negative ones. So there's a video on the full thing, but there was a lot going on in this workbook, so here's just a few quick examples. A rational exponent is an exponent that is a fraction, and we have two different forms. So you can see we have a fraction here, and the thing is this fraction has a numerator of 1. And then we have a fraction here, which has a numerator that isn't 1. So those are the two scenarios. You could have a fraction of a half, a third, a fourth, a fifth. All of the fractions that have a 1 as a numerator are very, very straightforward. And they're straightforward because of this beautiful flower I have down here. Now, unfortunately, this flower is in a jar and not on the ground because the rhyme is flower, power, and the top of the plant is the flower. And on the bottom of the flower, we have the roots, right? So the bottom of the flower is the roots. So it means that the bottom of the fraction, the denominator of the fraction, is the root, and the power is the flower. So the power is at the top. So this just means if you have a 2 to the 1/3, it means the root index is a 3. So it's not a square root, it's a cube root. And we have 2 to the power of 1 on the inside. How that changes with the one on the right here is that this is now my power. So it means we have, in this case, the 4th root of 3 cubed. Now, you are allowed to write it like this as well. The 4th root of 3 and then all cubed. Doesn't make a difference in the answer, but you'll see when we get to the video on simplifying these things, how you have it set up can make your life a bit easier. So we'll see the variety of usage in a future video. But that's the relationship. The numerator of the fraction is the power, and the denominator of the fraction is the index of the root. And then the base just goes underneath. So here we go. How am I going to convert this from an exponential to a root? Well, the base is 2. That is my root. So it is a cube root, and then to the power of 2. Now you could simplify this to say, okay, the cube root of 4. Looks better that way, right? If you can't simplify the radical, which will be a future video as promised, then you can just simplify it into a number because it just looks a little bit more appeasing to the eyes. So let's do 2 more. Now this one is a square root. When we have a square root, we don't write the index little 2, but we assume it's a little 2 there. So this just means we have 5 to the power of, well, 1/2, because my root is 2 and I don't have a power. Now if we look at 64, you might say, okay, well that just means 64 to the 1/5. And you're not wrong, but we can simplify that. I want you to get in the habit of looking at a number and considering whether or not it is able to be represented as a power. So when I see the number 2, 4, 8, 16, 32, so on and so forth, obviously 64, I'll put that up there. I know that those are all 2 to the power of something. When I see 3, 9, 27, 81, my brain goes 3 to the power of something. When I see 4, 16, 64, my brain goes 4 to the power. And this is my brain, because I've done this a lot, but this is where you want to get to. 5, 25, 125. Oh, that's 5 to the power. Because you can break a number down here. 64 is 8 times 8. And then I'll make this simpler rather than go 2 times 4. 8 is 2 cubed, and 8 is 2 cubed, which means 64 is 2 to the power of 6. So yeah, you have 64 to the 1/5, but you actually have 2 to the power of 6 fifth rooted, which means you have 2 to the power of 6 over 5. That is a lot better than that because your base is as simplified as it can get. So that's a little bit bonus detail for you there. Now, how about simplifying rational exponents? Like I mentioned, that connection between a base and knowing if it's an exponential, we can sometimes simplify. So here we have 8 to the 2/3, which means we have the cube root of 8 squared. Now here's an example of why it's beneficial to do it in one of the 2 ways here. Because if you want to simplify this, you would have the cube root of 64, and then you would be astute enough to go, okay, well, 64 is 8 times 8, which is 2 times 4, which is 2 times 4. So I actually have 4 times 4 times 4, right? Because the 2's can combine, which means you have 3 identical factors, which means you could simplify this all the way to 4. But it's easier in this one, because what's the cube root of 8, right? 8 is a cube root. So you do that first, because 2 times 2 times 2 is 8. So here the cube root of 8 is 2, and then it's squared, which again is 4. So you can see this way is easier because it keeps our numbers smaller. There's less work for us to do. So now let's look at this one. Here we have 625 to the negative 2/5, which means from our other exponent video, we have 1 over 625 to the positive 2/5, which means we have 1 over the 5th root of 625 squared. Now you can imagine you probably don't want to do 625 squared, because 625 times 625 is 390,625. So let's look at it this way instead and see if do we have the potential to simplify that. Well, 625 is 5 times 125, which is 5 times 25, which is 5 times 5. And you can see you only have 4 5s. So we're not going to get enough to break a 5th root. So don't even bother simplifying it. You can leave your answer as the 5th root of 625 all squared, because otherwise you're going to get a decimal number. This isn't a perfect rational. Now, if we had, I'll just do the if just so you can see it in action. Whoops, pardon my erase here. So you saw that, but if we had this as 625, let's say, do a brand new question, to the negative 3 over 4, for instance, well, then you're going to have 1 over 625 to the 3 over 4, which is going to give us 1 over the 4th root of 625 cubed. And we just saw over here that 625 is 5 times 5 times 5 times 5. So you have the 4th root of 625 is 5. So you have 1 over 5 cubed, which is 1 over 125. So if you can simplify it, that's why it's better to have the exponent outside of the radical. And if you can't simplify it, then it really makes no difference at all. And then the last one we looked at were these kind of loaded ones, but this is just bringing our exponent laws back from the previous section. So we are multiplying a common base, so we have 2, and then we add the exponents. So 1/3 plus 3/4. But remember, when we're adding fractions, we have to get a common denominator. So I'm going to multiply this by 4, and I'm going to multiply that by 4, and that by 3, and that by 3. So I have 4 over 12 plus 9 over 12, which gives me 13 over 12, which means on the top, I now have 2 to the 13 over 12. Whoops. 2 to the 13 over 12. On the bottom, I have 2 to the 5/6. Now, what do I have? Well, I have a division of a common base. So what do I do to the exponents this time? I subtract. So my exponents are going to be 13 over 12 minus 5 over 6. Can't do that. I need a common denominator. So times 2 times 2. So now I have 13 over 12 minus 10 over 12, which gives me 3 over 12, which simplifies to 1 over 4. So this actually simplifies all the way down to 2 to the 1/4. And if you wanted to convert this into a radical, you end up with the 4th root of 2. So you can see everything is now kind of tying together. I know it's a lot to remember, but the more you practice and the more you try this stuff, the more fluid it becomes, okay? So that's it. Consider all that. Lots of practice in the workbook, but as we move out of section 1 into section 2, it's going to get a lot more graphical and a lot more less exponents intensive. So don't stress yourself out if this is harder than you want it to be. Things are going to shift slightly, but always plug away, keep trying your best, and keep trying to learn. Great work. I'll see you next time.